For decades, our understanding of the universe has been built around a remarkably successful framework. Einstein's theory of general relativity describes gravity and the behavior of spacetime. The standard cosmological model adds dark matter and dark energy, while observations suggest that the universe began in a hot, dense state approximately 13.8 billion years ago. Yet in recent years, astronomers have uncovered several observations that are forcing scientists to examine some of their assumptions more carefully. One of the most famous problems is known as the Hubble tension. The basic idea sounds simple. Astronomers are trying to determine how quickly the universe is expanding today. But different methods produce different answers. Measurements based on the early universe, particularly observations of the cosmic microwave background, lead to an expansion rate around 67 km per second per megaparsec. Measurements based on nearby cosmic objects, including Cepheid variable stars and type Ia supernovae, have traditionally produced a value closer to 73. That difference may not sound enormous. But on the scale of the universe, it is significant. If both techniques are correct, then something about our understanding of cosmic expansion may still be missing. The James Webb Space Telescope has become an important part of this investigation because its infrared vision allows astronomers to examine distant and nearby stars with exceptional detail. Webb has helped researchers investigate the distances used in the cosmic distance ladder, including measurements of Cepheid stars. However, this does not mean Webb has disproved the Big Bang or demonstrated that Einstein's theory has failed. Instead, the observations have strengthened the scientific debate over why independent measurements of the expansion rate do not perfectly agree. And there is another mystery. Webb has discovered galaxies existing surprisingly early in cosmic history. Some of these galaxies appear brighter and more massive than astronomers initially expected to find so soon after the universe's beginning. At first glance, this seems to create a serious problem. How could complex galaxies containing enormous numbers of stars develop so quickly? But astronomy is rarely that simple. Early estimates of galaxy masses and ages can change when scientists obtain better observations. Dust, star formation history, stellar populations, and the contribution of active black holes can all influence how a distant galaxy appears. Some early claims about impossible galaxies have already been revised as better measurements became available. Nevertheless, the observations remain scientifically important. They tell researchers that galaxy formation in the young universe may have been more efficient, more rapid, or more complicated than earlier models predicted. And this leads to a much bigger question. Could our current cosmological model require modification? Scientists have proposed many possibilities. Some involve changes to dark matter or dark energy. Others explore modifications to gravity, unusual properties of the early universe, or new particles and physical processes. There are also more speculative ideas. Some alternative cosmological models have questioned whether the universe's apparent age, expansion history, or fundamental assumptions about cosmic evolution should be interpreted exactly as they are today. One proposal, for example, has suggested a much older universe by combining alternative explanations for redshift with changing physical parameters. These ideas remain controversial and are not part of the established scientific consensus. That distinction is important. Science does not change because one telescope produces a surprising image. A genuine revolution requires repeated observations, independent measurements, mathematical consistency, and successful predictions. But that does not make the current mysteries less exciting. The real story is that modern telescopes are allowing humanity to examine the universe with unprecedented precision. And the more precisely we look, the more complicated the cosmic picture becomes. The Hubble tension and unexpectedly early galaxies may ultimately be explained within existing physics. Or they could point towards something genuinely new. Either way, astronomers now have an extraordinary opportunity to find out. And the next question is even more fascinating. What if these apparent contradictions are not separate problems at all, but clues pointing toward a deeper understanding of space, time, and the evolution of the universe itself? The possibility that today's cosmological mysteries could share a common explanation has attracted enormous interest among physicists. But there is an important line between an intriguing hypothesis and an established discovery. The James Webb Space Telescope has not shown that the universe is broken. It has shown that our measurements are becoming precise enough to expose questions that were previously hidden by uncertainty. Consider dark energy. According to the standard cosmological model, dark energy makes up roughly 68% of the universe's total energy budget and is associated with the accelerating expansion of space. We still do not know what dark energy actually is. It could represent a property of empty space. It could involve a previously unknown field. Or, in more radical possibilities, our understanding of gravity on the largest scales could be incomplete. At present, none of these explanations has been conclusively demonstrated. Dark matter presents a similar mystery. Astronomers see evidence for additional invisible mass through its gravitational effects on galaxies, galaxy clusters, and the large-scale structure of the universe. But despite decades of searching, scientists have not yet identified the fundamental particle responsible for dark matter. That leaves open an important possibility. Perhaps our description of gravity or matter is incomplete. This is where theoretical physics becomes especially interesting. Researchers have developed models in which the properties of the universe could evolve over cosmic time. Some theories investigate whether fundamental constants might have behaved differently under extreme conditions in the early universe. Others explore modifications to gravity or additional fields that could influence cosmic expansion. There are even models involving higher dimensions or structures beyond the portion of the universe we can observe. These concepts are mathematically interesting, but they remain speculative. There is currently no confirmed evidence that our universe is being pulled by another universe or that a hidden dimension is controlling the expansion we observe. The same caution applies to the idea of cosmic time itself changing dramatically. General relativity already tells us that time is not universal in the simple Newtonian sense. Gravity and motion affect how clocks measure time. But that does not mean galaxies in the early universe secretly experienced billions of additional years while only hundreds of millions passed for everyone else. Such claims require specific physical mechanisms and observational evidence. Nevertheless, studying the early universe does force us to confront an extraordinary fact. The farther we look into space, the farther we look into the past. Webb is effectively allowing astronomers to observe galaxies from an era when the universe was still extremely young. These ancient systems are laboratories for testing theories of star formation, black hole growth, galaxy assembly, and cosmic evolution. If existing models successfully explain the observations, our understanding becomes stronger. If they fail repeatedly, scientists will have to search for better explanations. That is not a failure of science. It is how science works. Newton's laws were enormously successful, yet Einstein showed that they were not the final description of gravity. Quantum mechanics later revealed another layer of reality that classical physics could not explain. The same pattern could eventually happen in cosmology. Perhaps dark energy will turn out to be something entirely different from what we currently imagine. Perhaps dark matter will finally be detected. Perhaps a new theory of gravity will emerge. Or perhaps the apparent tensions will eventually be resolved through improved observations and better calibration. We simply do not know yet. And that uncertainty is exactly what makes this period of astronomy so exciting. Webb and Hubble are not destroying our knowledge of the universe. They are testing it. Every unexpected galaxy, every disagreement between measurements, and every unexplained cosmic pattern gives scientists another opportunity to examine the assumptions behind their models. The universe does not have to match our expectations. Our theories have to match the universe. So the biggest lesson from these discoveries may not be that the Big Bang was wrong, that dark energy is imaginary, or that physics has collapsed. The deeper lesson is that our current picture may still be incomplete. Humanity has only been studying the cosmos scientifically for a tiny fraction of its history. Now, with instruments capable of looking billions of years into the past, we are beginning to encounter questions that previous generations could barely imagine. The next breakthrough may come from Webb, Hubble, a future observatory, or an experiment that has not even been built yet. And when that breakthrough arrives, it may not simply answer one question. It could change the way we understand space, time, matter, and our place within the universe. For now, the mystery remains open. And perhaps that is the most exciting discovery of all.